Hello, and welcome back to the next recording session focused on sampling and an introduction to sampling. In the previous recording session, we looked at different sampling methods such as random samples or different types of samples, random samples, stratified random sample, this kind of thing, as well as a number of different descriptive statistics that people look at for samples, such as the sample mean, sample median, the variability statistics, such as the sample variance or range. And we did all these with the kind of getting us into the direction of, well, is a sample representative of the population that we're drawing from? And could we say something about, okay, if the sample mean turns out to be this value, can we project that on the full population? Is it representative of the full population, so much so that we could have some confidence in saying something about that sample mean in relation to the population mean? Something about that sample variance being, you know, what is it, how can we use that as inferring information about the population variance, the true population variance. Now we turn our attention to sampling distributions. And the idea of sampling distributions gets to this. So let's say today, let's say I look at a population. Let's look at the SAT scores, the admission scores for SMU students from 1930 until the fall of 2011. All the students that ever applied to SMU, excuse me, and then attended SMU, I think you would agree that that is a lot of different students. And if we actually had on record all of the different SAT scores that they came in with, and by the way, SAT, the exam itself, I guess, was created in 1926. So I'm assuming, let's say in 1930, SMU adopted it as one of the entry admission requirements and reviewed and such. So that's our population. All the SMU students, alumni, current students, as of fall of 2011, all the way back to 1930. I have all of those SAT scores. Now, suppose today I draw a random sample of 50 of those scores out of all that complete data set. I draw 50 of them, and I take the sample mean, and I calculate the sample variance, and I mark it down. I note what was the sample mean of those 50 observations. And then tomorrow I draw another sample, and I note the sample mean for that second sample, and I mark that down, and the same thing for the sample variance. And then on the third sample I draw, same size sample, 50 observations on each one, 50 data points for each one of those. And let's say I did that for 365 days. I did it in the entire year, a new sample every day. A new sample every day for the next 5 years. And if I logged each day those different sample means and those different sample variances, I could then come up with a probability, a distribution function associated with those sample means. I could look at that and say, okay, here is, I would be able to come up with a distribution associated with those sample means. I could come up with a distribution associated with those sample variances. And that distribution, those distributions are what are called sampling distributions. So let me read through here. For a particular sample, say x1 through xn, we can calculate values for that particular sample, x bar, the sample mean, and the sample variance. And there are obviously many different samples and associated with sample means and sample variances for each one of those different samples I could take. X bar and the sample variance turn out to be random variables themselves with their own probability distribution. That's what we would be looking at. Is what is the distribution of the sample means? What is the distribution, probability distribution associated with sample variances? Again, we're drawing from a particular population, a particular probability distribution function. The random variable itself, the underlying one, would be the SAT scores. But I'm going to be drawing samples of size 50 and looking at those sample means. That sample mean, it in itself is a random variable. So that's the sampling distribution. Long-winded way of saying it. Sorry about the going on and on. But it is a very, very important concept that you get. This again, just to restate it as I always do on these recording things, this is your first brush. This is a first glance. We'll talk more about it in class together. We'll go through the exercises. I also refer you to the textbook for the sections on sampling distributions to read through that as well, to really make sure you have this concept. We will be using this quite a bit in the future topics that we're going to cover, because it is one of the foundation of doing things like hypothesis testing, confidence intervals, so forth, that we'll cover here shortly. Sampling distribution of X bar with a known population standard deviation. So again, let's say we had all of those from 1930 to fall of 2011. We had those SAT scores. Suppose for some reason we know the population standard deviation associated with all those different SAT scores. Okay, we're going to peel that assumption back. We're going to start out with a load of assumptions, and then we're going to relax them as we go on here. Okay, so let's look at this. If x1 through xn is a random sample of size n from a normal distribution, let's look first at normal distributions with a mean of mu and a known standard deviation sigma. And if x bar is, just as we talked about before, a sample mean where you add up the values in the sample and you divide by n, the size of the sample, then what does the probability distribution function look like for all those different x bars, all those possible sample means that you could take from this underlying distribution, this normal distribution? Well, it turns out that the probability distribution of those sample means would also be normal, and it would have a mean of mu, the mean of the sampling distribution of sample means would be the same mean as your underlying distribution that you're drawing from, and the standard deviation for this distribution of sample means would be the standard deviation of the population you're drawing from divided by the square root of n. And the way I kind of think about that standard deviation of x bar is the way you could write it, standard deviation divided by the square root of n. So we have this normal distribution with a mean mu and a standard deviation sigma. If we drew one observation out of that, and we've been doing that, what's the probability that that observation value falls within one standard deviation of the mean, or falls within 5, plus or minus 5, a value of 5, whatever, of the mean? We've looked at that in the during the continuous probability distribution function work that we've done with exercises and such. In this case, we're not just drawing one value from that underlying population, we're drawing n values. And with those n values, we're looking at the sample mean. So if we draw 50, not just one, but 50 different values, and we take the mean of those values, and then the thing is that the sample means are going to be they're going to be more focused around that mu than just one observation. And again, I'll go back through this while we're in class together. But imagine you take 50 observations, n is equal to 50, and you're looking just at the sample means. You take samples of size of 100, you're getting more information as n gets larger. So your variance, your standard deviation is getting smaller and smaller, right? Because n is getting larger. You can see that by the standard deviation divided by square root of n for the sample that you've drawn. So that's intuitively, to me, that's what's going on with this. One observation, you got a fair amount of variance. You got sigma as the standard deviation. But if you take a sample of 50 or 100 different observations and take the sample mean, that sample mean is more likely to be, have less variance to it and go around U than one observation. Okay, move on. Okay, so Z, as we've had before, standard, the sample mean minus mu, because mu is now the mean of the sampling distribution of X bar, divided by the standard deviation of the sampling distribution of X bar, which is now sigma over the square root of n. This follows a normal distribution, 0, 1. Let's look at an example of this. The dollar amount per transaction, X, in the sporting goods department of a store has a normal distribution with a mean $75 and standard deviation of 20. What is the probability that a random sample of size 9 sales transactions will have an average over $85? So we're interested in the dollar amount per transaction. We know that on average it follows normal distribution with an average sale of $75, standard deviation of $20. We draw a random sample of 9, and the question is, what's the probability that the average of those 9 sales transactions will be over $85? So we know the underlying distribution of sales transactions follows a normal distribution, has an average of $75 per transaction, standard deviation of 20. We also know now that the distribution of the sample means, repeated drawing of samples, looking at those sample means, all those different samples that you could possibly take, they would end up following a normal distribution, same mean, $75 per transaction, per average. That would be your average of all those means, sample means, and the standard deviation associated with this distribution would be 20, which is the standard deviation of the population, or the population you're drawing from, the distribution you're drawing from, and we were taking sample sizes of size 9. So what's the probability that the sample mean? A sample mean would be greater than $85, and that's just working through and saying, okay, that's working with the Z distribution, the Z calculation transformation. 85 minus 75 is 10, and we're looking to find how many standard deviations above the mean is 10, and that's divided by the 20 divided by square root of 9, and we're looking for, we find that would be the same as the probability that Z is greater than 1.5, and therefore it's 0.0668 that we would draw a sample that would have a mean above 85. Central limit theorem. Okay, so this is a very big theorem in the statistics domain. Let's have a look at it. If X bar, the sample mean, is the mean of a random sample of size n, x1 through xn, from a population mean with mean mu and a finite standard deviation sigma, then if n, as it goes to infinity, the limiting distribution of Z is a standard normal distribution, Z as we defined it in the previous